named after a famous mathematician with the last name Riemann. So we've seen so far the lower sums. This should be a capital S. I don't know if I got it changed in your notes or not. But we use the little s for our lower sums. And we use the little c to represent the lower value of the interval. We use the big S for our upper sums. And the big C for the upper value in the interval. And we've already seen that if you did the limit to infinity, both the lower sums and the upper sums approach the same number. That would be the area. Okay? And the following things needed to happen. We needed to have a continuous function on a closed interval. So far, we're only dealing with non-negative, nothing going below the x-axis. So all of our rectangles were above the x-axis. And we divided our interval into n sub-intervals so that we could figure out the change in x is whatever the distance was between a and b divided by n. We've got our absolute minimum with the little c and the absolute maximum with the big C. So the idea now is that between the lower value and the upper value, there's going to be another number in the middle or anywhere in the middle that we're going to call u. So you have a smaller rectangle, a bigger rectangle, and then one rectangle in the middle. And since the change of x is greater than 0, right, because we're doing it as it goes to infinity, it's never equal to 0, but getting smaller and smaller and smaller, we would have all of these inequalities still being true if you multiplied by the change of x. And if you added them all up, they would all still be true. Now we know that the smaller ones make the lower sum, and the bigger ones make the bigger sum. So we know that in between is another sum that would be between the lower sum and the upper sum. But we've already discovered that if you make the limit as n goes to infinity of both the upper and the lower, they're both equal to a. So by the squeeze theorem, remember the squeeze theorem? We haven't squeezed the theorem for a while. By the squeeze theorem, that means this one in the middle also has to equal the area. And this is what Riemann was sort of looking at. He was saying, it's kind of annoying to have to figure out the lower ones and have to figure out the upper ones. But if we use the squeeze theorem, it actually doesn't matter which point we use. Any point in that interval for the height of the rectangle will work. Because if the lower ones go to the area and the upper ones go to the area, by the squeeze theorem, any one in the middle will go to the area as well. So we call any of those sums Riemann sums. Same property, we have the function defined on the closed interval. But what Riemann was able to do is it doesn't necessarily have to be continuous, and it doesn't necessarily have to be always positive. And you don't necessarily even need to make all of your widths of your rectangles the same width. So what Riemann was doing is he was playing around with this and saying, what are the things that have to be true and what doesn't have to be true, and what can we do to make that work? So he is also saying we don't have to use the left value or the right value, we can use any value. And what this did for our intervals is it simplified things because it could say, well, let's just always use the left endpoint and always use the right endpoint. Because it was frustrating when we, like even in our notes, we made mistakes with our notes. Because it was frustrating, like, oh, which side is the lower one, which side is the upper one? So much figuring has to be done. And if you make an infinite amount of rectangles, that's an infinite amount of figuring things out, which we don't want to do. So Riemann said, well, since any value works, why don't you just do one with the left side? And why don't you just do one with the right side? And we get a left Riemann sum and a right Riemann sum. You could even use midpoints. And there's the midpoint Riemann sum. So we'll start off with a nice easy one, x squared minus 3. We're doing the left Riemann sum, so that means every time we choose a point, so for rectangle number 1, we use the left point. For rectangle number 2, the left point. For rectangle number 3, the left point. Rectangle number 4, the left point. And we even have different widths. Some rectangles have a width of 1, some rectangles have a width of 2. So our first change in x has a width of 1. Our second change of x has a width of 1. Our third one has a width of 2, and our fourth one has a width of 2. Our first point, f of 0, is negative 3. Our second point would be f of 1. That one's going to be at negative 2. Our third point is f of 2. And our fourth point is f of 4. So in green here, in each interval, we're using the left x value for the left Riemann sum. So now we have to add up all of these rectangles. In sigma notation, it would look like this. So we're figuring out, I shouldn't use u, because it always feels awkward when I want to say we have to figure out fu, and multiply it by the change in x each time. You can write that out if you want. But we get an area of 23. Something to notice in our calculations, which we've talked about a little bit before, is that these rectangles that were below the x-axis end up having a negative answer. Their areas are represented by a negative area because it's below the x-axis, and the other ones have positive areas. So that's a left Riemann sum. Our next example uses midpoints. So we have the same intervals, but now your y value is always by plugging in the middle point. So the widths are the same as in A. But now we would have to look at the midpoint of each interval. And this time, we get 52.5. And once you're finished writing that down, I want you to look at the left one and look at the mid one and ask yourself which one in this situation do you think is a better estimate for the actual area under the curve. And remember, when we say under the curve, just like the video that we watched at the beginning of this unit, under the curve is the area between the curve and the x-axis, with any areas below the x-axis as negative and areas above the x-axis as positive. So as far as estimating goes, if you wanted to figure out the actual area, can you see that this lower one counted extra negatives here, but didn't count nearly enough positives on the right-hand side? Okay, so for the actual area, what did we come up with this one? We came up with 23. For the actual area, we would have needed to added more and subtracted less. So this is should be lower than it should be. For the midpoint one, where we got 52.5, I kind of like the midpoint because here we have a little bit too much negative, but we would have missed some negative there, so it's kind of compensated. Same thing here. There's a little bit extra negative there, but we missed some negative there. In this section, like this and this, almost looks like you could cut that out and fill it in pretty good. Same thing with this section and that section. The extra that we counted kind of looks almost nicely to fit perfectly into the part that we missed out. So this seems like a better estimate, okay? I did some mental math. The actual area is 54. And no, I didn't add up an infinite amount of rectangles. Theoretically, I did with a shortcut. We're going to very nicely, just like with definition of the derivative, remember that limit thing that we used to have to do? And now we have all our derivative rules and can do it much shorter. We are going to learn a shortcut for area under the curve as well. Unfortunately, in true calculus spirit, this is what when you go to university, in true mathematical spirit, I can't, in good conscience, tell you the shortcut without painfully showing you all the work that previous mathematicians had to go through to discover it. When you go to university, that will be the mentality of your university professors all the way through. And so if something is really painful in university and you're like, I don't get what's going on, most likely it's leading up to a shortcut which you'll be able to do, and possibly, although we would like to think you don't forget the methodology that led you to it, but you will. You will forget about these little rectangles and Riemann sums of left and right, because you're like, why would I do all that work if I could do the shortcut? So we have to painfully go through some of this rectangle stuff first, and then I will show you how I use the shortcut to get 54 with mental math without adding up a bunch of infinite rectangles. But we're not there yet. A little bit more pain first. Okay, so now we've got x cubed, x squared plus x plus 2. The parabola is nicely drawn for us there. And we're going to use the left Riemann sum, so that means every time we're using the left points, just as a visual, I think this is going to be an overestimate, because it seems like the extra area that we counted in those rectangles is more for the area that we missed. But again, This time, all of our changes in x are equal, so they're all a half. And if they're all a half, our left endpoints are 0, 0.5, 1, and 1.5. We can write out our sigma notation for this. Maybe because this is long, it's appropriate that we use u and have to have fu in the equation all the way through. So I got 3.75, and I felt like this was an overestimate because I could see a picture of the graph. Tedious even when we just do 4 rectangles, right? We haven't even got to close to an infinite when we're at 4, and we're already tired. Here's the right one. Again, I'll give you some time. Now we're using the right endpoints. Looking at the diagram, it looks like an underestimate at 2.75. But by doing the left and the right and looking at the diagram, I'm like, I feel confident it's somewhere between the 3.75 and the 2.75. So what we're doing right now, as you're writing this down, we're sort of going through a history of the thought process that the mathematicians went through at the time. They're like, starting with lower and upper, because that really makes sense that if I have one for sure I know is below and one for sure I know is above, then my actual one has to be between. Okay? And then getting annoyed with the lower and the upper because, well, which points do I use? So Riemann comes along and says, well, actually, if you use any point in there, if we do it to infinity, it doesn't matter. So now, oh, that makes it a little bit easier because it doesn't matter which points I choose. So then it became simplified, is that, well, if you want to get an estimate, you could do the left side and the right side, and then know that it's probably going to be somewhere in between there for an approach. Okay? And then someone was like, well, left side and right side, why don't we do the midpoint? So here's your midpoint one. Maybe. And the midpoint one, looking at the picture, that's kind of nice because every time you overcompensate on half the side, you undercompensate on the other, so it kind of looks like it averages out. This looks like the best estimate so far. 3.375. Our process right now is just coming up with better and better ideas of trying to get this area as accurate as possible, as quick as possible. This one at 3.75, or 3.375, seems to be the most accurate of the three. Okay? Moving forward, there's going to be another mathematician that we're going to get to today that's going to say, well, what happens if we just use the endpoint and made trapezoids? And found the area. Oops, that's not the endpoint. This endpoint would be there. And find the trapezoid of each one. Wouldn't that be even more accurate? Trapezoids are almost like the tangent. It's the slope of the secant through the endpoints. And if you make it smaller and smaller, oh my goodness, that's going to get to tangents, and that's our derivative again. Whew. Sorry, got a little excited there. I'm getting ahead. Slow it down. We're just going to deal with rectangles. Do another rectangle one. This looks like a nice AP style of question where they give you a table of values. It's continuous on the closed interval from 0 to 12. And you have values shown in the table above. Use the midpoint Riemann sum with 4 subintervals of equal length to approximate the area under that curve from 0 to 12. First of all, let's do the easy math. If they're equal length, how wide is each subinterval? Four subintervals from 0 to 12. Good thing is my mic isn't that strong. They're each 3 wide, right? Yeah, awesome. And then, those would be our 4 subintervals if we're using our midpoints. Right, midpoint of this one's 1.5, 4.5, 7.5, 10.5. So if we take the midpoint, find that height, that's your y value, multiply each of those midpoints by 3, because that's the width of your rectangle. We get 125.4. So if you wanted, you could draw out those points, draw the rectangles, get an idea